Okay, continuing to work with f of x equals e to the 2x, I now want to find a degree 3 polynomial that will approximate or impersonate f of x equals e to the 2x. So I need to compute the first 3 derivatives of f in order to create a third degree polynomial. So let's see, I'm going to have f of x, which is e to the 2x, and then I need f prime, f double prime, and f triple prime. Okay, so f prime is 2e to the 2x, then 4e to the 2x, then 8e to the 2x. And I'm going to plug zeros in for all my x's. So I get 1, 2, 4, and 8. Okay, now I need to do the same thing for P3. So P3 of x is a naught plus a1x plus a2x squared plus a3x cubed. P3 prime is going to be a1 plus 2a2x plus 3a3x squared. P3 double prime is 2a2 plus 6a3x, and P triple prime is 6a3. And now I'm going to plug 0 into all of these, and I get a0, a1, two a2, and 6a3. So what do the values of a0, a1, a2, and a3 need to be? I need to set the function values equal to the impersonating function values. So f of 0 has to equal p3 of 0. So that means that 1 has to equal a0. This has to equal this. And 2 has to equal a1. And 4 has to equal 2a2. And 8 has to equal 6a3. So to solve these, first two are really easy, they're already solved. And then 4 equals 2a2, that tells me that a2 has to be 2. And 8 equals 6a3 tells me that a3 has to be 4/3. And then my final answer is to write out a function where those are the coefficients. So p of x is a0 plus a1x plus a2x squared plus a3x cubed, and then replace the coefficients with the numbers we just found. So it's 1 plus 2x plus 2x squared plus 4/3 x cubed. All right, compare the values of a0, a1, and a2 for the quadratic and the cubic approximating function. So if we just look at the first 3 terms of this cubic approximating function, that is exactly what we got when we did the quadratic approximating function, 1 plus 2x plus 2x squared. So they are the same. So if I want to find a formula for P4, the Taylor degree polynomial of degree 4 for f of x equals e to the 2x near 0, I just do this whole process again, but I've done most of it, right? I know f of 0 is 1, and f prime of 0 is 2, and f double prime of 0 is 4, and f triple prime of 0 is 8. And if I want to know the fourth derivative of f, I need to start from the third derivative, which I already took. F triple prime of x was 8e to the 2x. So the fourth derivative of x is 16e to the 2x, and I plug in a 0, and I get 16. So that's my only new value here. And then I need to set that equal to the fourth derivative of P4. So P4 is going to be a naught plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth. Now, the first three terms are set, right? I figured those out when I did P3. So this part is done. I already know that a naught is 1, a1 is 2, a2 is 2, and a3 is 4/3. I just have to figure out what a4 is. So I'm going to do the first four derivatives of a4x to the fourth. So P4 prime is some stuff plus 4a4x cubed. P4 double prime is going to be some stuff plus 12a4x squared. P4 triple prime is some stuff plus 24a4x. And then P4 fourth derivative is some stuff plus 24a4. So to figure out a4, I need to set that equal to that. And when I take the fourth derivative, that all the stuff is going to be 0 in my fourth derivative of P4. Okay, so I'm going to set 16 equal to 24 a sub 4, and you get a sub 4 is 2/3. So my final P4 of x is 1 plus 2x plus 2x squared plus 4/3 x cubed plus 2/3 x to the fourth. Okay, so I've plotted f of x, which is sketched in red here, e to the 2x. And then I've plotted the first four Taylor polynomials. P1 is the line, this line here, just the tangent line at x equals 0. And then P2 is this green quadratic. And then P3 is this cubic that's a blue dashed. And then lastly, I have P4, which is this quartic in orange. So what we should notice about these is that near 0, all of them are a really good approximation if I'm really close to 0. But I can get further and further away, and you'll notice that this green quartic, the orange quartic, starts approximating the red function really much further than anything else, much further away from 0. And it continues to approximate the red function for a really long time, like all the way up until here. The red and the orange are practically on top of each other. So that orange function, when you're between, say, negative 0.75 and 0.75, is a really good impersonator of e to the 2x. So these approximations get better and better. They agree over larger intervals. Okay, so here's the general formula for a Taylor polynomial of degree n. We already found P4 for e to the 2x, but now we're just going to use this more algorithmic formula approach to find it again. So I want to find degree 4 near a equals 0, so I'm going to fill in this template. If I want a 4th degree polynomial, I need 4 derivatives, so I start by taking all 4 derivatives of f. And then I plug 0 into all of them, so I get 1, 2, 4, 8, 16. And then I'm going to plug in those values into this formula for the Taylor polynomial of degree n. And I should notice the fact that 0 factorial is 1. So f of 0 over 0 factorial. Well, f of 0 is 1. 1 over 0 factorial x to the 0 plus f prime of 0 is 2. F double prime is 4. F triple prime is 8. And the 4th derivative is 16. So this would be over 4 factorial x to the 4th. Now I'm just going to simplify these fractions. 0 factorial is 1. 1 over 1 is 1, and x to the 0 is 1. So this whole first term is 1. And then 1 factorial is 1, so this is 2x. And then 2 factorial, that's 2 times 1, so that's 2. 4 over 2 is 2x squared. 3 factorial is 6, that's 3 times 2 times 1. So 8 over 6, that is 4 over 3x cubed. And 4 factorial is 4 times 3 times 2 times 1, which is 24. 16 over 24 reduces to 2/3. And this is exactly what we got by just matching derivatives. Okay, another example. We can do Taylor polynomials that are centered at values other than 0. So we make them match, instead of at 0, some other x value, which we'll call a. So this is my formula for when the place that we're matching derivatives is a instead of 0. So we're going to do a Taylor polynomial of degree 6 for cosine x, and we want them to match as close as possible at the x value a equals 0. So I start by taking 6 derivatives because I want a 6th degree polynomial. So the derivative of cosine is negative sine. Derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of sine is cosine. The cosine is negative sine. And the derivative of sine is cosine. And then I plug 0, and then I'm going to plug pi into each of these formulas. So the cosine of pi is negative 1. The sine of pi is 0, so negative 0 is 0. The cosine of pi is negative 1, but this is negative that, so it's positive 1. 0. The cosine of pi is negative 1. And now these things start repeating. Now I'm going to plug all these values into my formula for the Taylor polynomial. So f of a, that is negative 1. A is pi. F prime of a, that's 0. And this is pi. F double prime at pi is 1. A is pi. And then F triple prime of pi is 0. And that's all I've got written out. So I'm going to start plugging in here. So negative 1 over 0 factorial, that's negative 1 over 1, which is negative 1. X minus pi to the 0, anything to the 0 is 1, so this first term is negative 1. My next term, this term here, is 0 because it's 0 times times some stuff. So just do that. And then my next term, I have 1 over 2 factorial times x minus pi squared. The next term is 0. My next term is going to be the fourth derivative at pi, which is -1. And then my next term is going to be 0, the fifth derivative. And my last term, sixth derivative at 0 is 1. So this is 1 over 6 factorial times x minus pi to the 6th. So I don't really need to write these plus zeros. So I'm going to do -1 oh, I messed something up. Okay. The 3 factorial, okay, so this term was 0, which means that this term is supposed to have 4 factorial and 2 to the 4th power. And then the 5th term is 0, and then the 6th term. Okay, good. So this is 1 over 4 factorial times x minus pi to the 4th plus 1 over 6 factorial times x minus pi to the 6th. We can use Taylor polynomials to estimate values of functions and also to estimate integrals. So earlier, just now, we approximated e to the 2x with a 4th degree Taylor polynomial. I'm going to use this to estimate e squared. So e squared is the same thing as e to the 2 times 1, which is the same thing as replacing that x with a 1. So this should be approximately equal to the Taylor polynomial, where I replace each x with a 1. 1 plus 2 plus 2 plus 4/3 plus 2/3. So 4/3 and 2/3 is 6/3, which is 2. So 2, 4, 6, 7. So e squared is approximately 7. How we get a better approximation for e squared? Use a higher degree Taylor polynomial. Okay, so now we're going to evaluate an integral by replacing a difficult function with a Taylor polynomial. So I want to do this impossible integral, sine x over x. There's no technique that's going to help me with that. So I'm going to replace sine of x with its 7th degree Taylor polynomial. So the integral from 0 to 1 of sine x over x dx should be approximately the same as the integral from 0 to 1 of p7 of x over x dx. So instead of sine, use its approximating polynomial. So this is the integral from 0 to 1 of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial all over x. I am going to simplify this fraction by dividing x into each term in the numerator. So this x over x is 1. X cubed over x is x squared. And then this becomes x to the 4th over 5 factorial minus x to the 6th over 6 factorial. Oops, 7 factorial. And now I'm going to integrate term by term. So the antiderivative of 1 is x, and this becomes minus x cubed over 3 times 3 factorial, plus x to the 5th over 5 times 5 factorial, minus x to the 7th over 7 times 7 factorial. Evaluate all of this from 0 to 1. When I plug in a 1, I get 1 minus 1 over 3 factorial is 6 times 3 is 18. 1 over 5 factorial times 5 is 600. And 7 factorial times 7 is 35,280. And this comes out to approximately 0.946.